have to simply say good day because it's 2 o'clock and I'm in India, so good day is what it'll have to be. Regardless, let's talk about glacier depletion, ice cover loss at the Arctic, and potential linkages to the Himalayas. This is my mantra. I have to include it in virtually everything I do, but I am just terrified in terms of looking at the future, in terms of wasting water, because we're going to run out. So my presentation, I'm going to have 6 areas. One and two are really just background. I will be going through them quickly because we're pretty much aware of everything, but just providing some magnitudes to, provide some context in terms of impact of water demands and groundwater withdrawals. The third section will be decline in land glaciers, and I'm going to use some information in terms of Canada because it's hot off the press. We've just finished it a matter of a few months ago, and it's very strong and indicative of something that I'll address when I get there. And then glaciers in the vicinity of India and the overall implications from melting land glaciers. And then I'm going to move into the Arctic ice disappearance, and this is something that we've got to, as a scientific group, we've got to figure out better what we're doing, because this is very ominous, and I will try to show why the polar vortex impacts and how that translates to summary of findings to date. So that's where we're going. So evidence climate change is widespread and intensifying. Everybody knows this. The water availability. We are now into the Anthropocene. This is the first geologic time frame where we have actually, as humans, influenced the environment. In other words, up until the Anthropocene started, we were really having a situation where we would adapt whatever we needed to be able to exist with that environment. But now we're at a stage where, unfortunately, we are now influencing that environment. So water availability, storms, groundwater, interbasin transfer, and so on, and glaciers, in many respects, we are out of options in terms of having water availability. Intense rainfall, destructive storm surges, hurricanes intensifying, increasing scarcity of accessible potable water. We know that those are all happening, so I'm not going to really comment other than simply acknowledge that, gee, we've got to start really getting some better understanding of what to do about these issues. But let's leave it at that, just being aware of that issue. This also is pretty much well known. In Canada, we play ice hockey, and so this is called a hockey stick where I come from. And what we just did is recently passed 8 billion people. Okay, it's obviously enhancing and increasing and so on, but what's really relevant is the rate of growth of water. In other words, while we have observed population growth doubling, the water use has tripled. Well, that's been okay because we've been able to accommodate that situation. But as we go further and further along, we're not going to be able to do that again, simply because there is not sufficient water to be able to do that. Okay, so why is that actually happening? Well, so the water use has been tripled. Okay, why? Well, demand for water will continue to increase dramatically. Why is that happening? Well, in part, and this is only one part, but it's important in terms of acknowledgement, the changing due in part to the habits and the diets that make very big differences. So, for example, if you look at China, the Chinese meat consumption went from 20 kilograms per year in 1985 to 50 kilograms per year in 2009. So what happens when that translates is when you look at the water needs to generate 1 kilogram of grain, it's 1,000 liters. But 1 kilogram of meat is 15,500. And once people become accustomed and desiring that, it's very difficult to get them to change back to the situation of what they had historically. So the rate of growth of water use is escalating dramatically, but as I intend to show very quickly in the next few slides, is we don't have the opportunity to do that again. This one, it's obvious we're getting incredible heat, and the 40 some odd degrees that it is outside here in India is a further indication of that, but that's just simply the way it is. Okay, so demands for megacities, well, we're getting many of them. It's very difficult to define the number of megacities, but I'm going to use this 10 million. Definition, slightly variation, you get more or less than 40, but nonetheless, concentrated areas of huge water demands. By 2050, we expect 70% of the population will be in cities. Where are we going to get the water for these people? 12% of the world population, they're living on the coastlines. And just to go back to the present, we have 10% of the world population living on coastlines. But as we move forward, we're going to get 12%, so a bigger percentage, but it's also of a bigger set of people. So therefore, coastlines, big issue because that's where people want to live. There's business opportunities, recreation, and so on. Given the coastline, concern with rising sea levels. That's obviously a real concern, but that's not the only concern, as I'll be trying to point out more specifically. This kind of diagram is very common. Weather disasters, 1980 to 2006, we could plot them for virtually anywhere. So again, we don't need to dwell on these, but we're seeing clearly more damages, more events happening, and more consequences as a result. How do we actually unfold this to understand better how to protect the situation? Well, one of the ways is to do groundwater withdrawals. And in the situation, I'm standing there at the side of the canal that brings the water down from the Ganga to Delhi. We were able to do that, and that's fine, but that opportunity is disappearing very quickly, overall becoming increasingly challenging to accomplish that. Now, if I go to the China, south to north diversion system they've spent $20 billion. It's taken 50 years, and 300,000 people were resettled. That's not something that we can do in very many locations. First of all, the expense, the time frame, and then the resettlement of people is not an easy undertaking. So what we've really got is how much water are we now using in terms of groundwater withdrawal? And this is a very informative map, I think, or figure, showing the degree of rate of change of India's withdrawal of water. Back in the 1960s, when the starvation was ongoing, they could not produce enough food, etc., the crisis was there. And what happened was they came up with the idea of the electric pumps, oil engines, etc., so that the water could be used to irrigate. But there were very few controls in place. And as a result, and you can see over the 1960 through to the present time, the number of pumps has been dramatically increasing. So India now has the highest groundwater usage in the world by a lot. They had 1 million tube wells in 1960 and 20.3 in 2005, and it's continued to escalate. What's the consequence of that? Well, they are able to provide significant needs of the irrigation. But the groundwater, for example, and I just got a couple of examples, but Gujarat, the groundwater levels 50 years ago, they were 10 meters below ground surface. Now they're 500 meters. Karnataka, 20% of the tube wells are going dry every year. And the implications, well, then these are just a couple of examples, but the groundwater levels are declining. There's increased energy needs to bring that water from such a significant depth up to the surface. The water quality concerns, as the groundwater levels decline, become poorer, and subsidence. And we cannot forget the last one of those for sure. So here's an example of just a series of 4 areas, but China, India, Latin America, Caribbean, and Sub-Saharan. The black on the left is the sustainable yield as projected for that particular area. And you can see the gray in 1995 and the without just white, I guess we'll call it, in terms of how it is going. For example, in China, they are now taking in excess of the groundwater withdrawals, which are sustainable. But in the case of India, dramatically more so. The other areas, well, they're doing okay, as it turns out, albeit we're not really addressing that at this point. Well, what happens obviously is the groundwater, 0.1% is replaced each year. So as we remove a great deal of water from the soil, the residency time of those water is approximately 1,000 years. So it's not being replenished. It is far from it. Okay, so what's that mean in terms of subsidence? Well, India now exceeds coastal absolute sea level rise by a factor of 10 for many coastal cities. So not only are the sea levels going to rise, but the land is going to subside with the utilization of so much of the groundwater. So every meter drop in the groundwater level translates to approximately 3.3 centimeters of subsidence. Hence, and I'm not going to read all these, but you can foresee really 21 major cities in India are poised to run out of groundwater soon. And these are just a list of some of them. Where are they going to get the water for all the people? Lucknow got massive subsidence, Kolkata subsiding at 13.5 millimeters per year, and so on. Well, clearly groundwater is in trouble. We don't have as much as is needed, not even close, and it will not recover. And we'll leave that discussion quickly at the end. But now let's talk about temperature. And clearly you can see that this is not surprising to see the temperature changes over a period of time, but this is all of the years in which relative just showing what's actually happening. But I just got to get that out of the way. All of the 10 warmest years were in the last 12 years. In other words, there's no question. I mean, there are some people in the world, like that former president of the country to the south of Canada, seems to think that it's not a worry, but he's one of the few in the world that's as dumb as that. So this is continuing and so on. And keep that in mind because I'll come back and talk about this escalation in a few minutes. So as a result, there is huge issues in terms of the, trying to get this thing out of the way, huge issues in terms of the cities that are exposed to excessive levels. These are cities only including those more than 1 million in population, but the distribution of them is obvious. Obviously, some is in North America, many in Asia, many in Southeast Asia, and so on. So this is a huge, huge worldwide problem. What's happening? Well, all right, as I've already discussed, we've got limitations in the groundwater availability. We've got limitations in the interbasin transfer. Yes, you can do it in some locations, but not very many, and it's becoming increasingly difficult. Turkey doing the dams are decreasing the amount of water that's available to downstream countries and all sorts of issues. So interbasin transfer, increasingly difficult, and massive urbanization and surface water, and we need to have enormous volumes of water for megacities. Okay, well, let's now turn to Canada, just for a few minutes at least, and look at groundwater insufficiency in central Canada. And a lot of people don't realize that Canada's in trouble. Profound importance of the river flows in Canada as depicted here. The map on the left is clearly Canada. The prevailing winds are from the ocean onto the shore of British Columbia, the western portion, and then as they impact by having to rise above the Rocky Mountains, they drop their precipitation. So what actually happens then when we look at this area here, so this is British Columbia, Alberta, Saskatchewan, if you happen to know the terrain, this has a great deal of precipitation in form of snow and rain. All right, well, that's extremely important because that's where the water comes from in all of this South Saskatchewan and North Saskatchewan rivers. This is the only major conduit by which there is water available to an area of Alberta and Saskatchewan. Not that it matters to you the names, but specifically, that's where 70% of the agricultural production of foodstuffs comes from in Canada. So we are a massive producer of food, but now we're seeing something, which I'll explain in a second, but is seeing declining levels of water being available for purposeful use. So what's actually happening? Well, here's the Peta Glacier, and this is just one of thousands of glaciers. I'm not trying to imply that, but it's one that we've studied in particular. So here it is. Here's the British Columbia here in the mountains, and here's this Alberta, Saskatchewan, and so on. And again, in the lower screen, it's just showing the particular location, but that doesn't, it's not really important other than it is an indicator of what's happening in the glaciers. So now let's go back to here. So now what's happening is we're trying to grow all these things with this during the food, the period where there's food growing, in other words, the summer period. So if we look at, and this is actually, I think, the longest record that exists in North America, but it lasts from 1902 up till 2007. So if you look at the, and I'm colorblind, but I'm pretty sure this is blue. This is the amount of precipitation, total precipitation, that is happening. The good thing is that it's not actually decreasing or increasing dramatically. Certainly there's fluctuation. But now let's look at the other two. This one here is the declining snowfall rate, and the blue one is the increasing rainfall rate. So what we're seeing with climate change is basically the same amount of water falling from the sky, but what form is it in? Well, if it falls as snowfall, it's there as a reservoir. It's there as a kind of a built-in natural reservoir, but that's declining. We're going down from roughly 300 down to 100 in the next, historically, in a matter of a very short period of time, 30 to 40 years. So what's going to happen is the August flows, part of the significant growing season. This is again over 1911 up to up to the present time. And what you see is there's obviously a decline in the amount of water that's going to be available in time. Similarly, September, another important dimension of the growing season. So we're going to have a lot less water available at the times we need it. And we don't have the opportunity to actually store this water very effectively because you're in mountains. Now we look at the Peyto Glacier, the one that I referred to just a few minutes ago. If we look at 1990, this is all from Landsat imagery, 1990, 94, 96, etc. What you can see as you progress through this diagram, this series of years, is that the Peyto Glacier is disappearing. What we're going to have is less water in the future going to the area where we grow so many things in Canada. So not only is the snowfall changing, no longer is it a battery up there with a whole bunch of water that we can assume that we'll have available later during the growing season. It's already melted, but also melting are the glaciers. And spatial dimensions of it, this is the snow cover area of the Peyto Glacier. And you can see by the dotted line showing how it's changed from roughly 350 down to about 150 in a matter of 30 years. The battery or this reservoir, the natural reservoir, is changing rapidly. So 70% of the agricultural production in Canada comes from Alberta and Saskatchewan. And this is not dissimilar to many other locations, clearly Western Canada, Europe, South America, etc. Peak watermelt impacts include, we're getting peak melting rates. They've already occurred in many situations, and they are going to continue to decline. So the meltwater will decline. Okay, it's now and this is more because of it's a tourist attraction, but it's now predicted that in all glaciers in the Yellowstone and Yosemite parks in the U.S. will be gone by 2050. Groundwater, what we're already seeing is it's declining in many countries. The land glaciers are disappearing in many countries. What are we going to use for water as we move forward? So what about the huge glaciers in the Himalayan regions? Well, this is just a schematic, and I have to move this thing again to get it out of the way. This shows around, obviously, India, Pakistan, etc., but it shows the contributing area for glaciers. There's 90,000 glaciers that feed the Indus River. Then the Amur Darya that comes up here that ultimately flows to the Aral Sea, and clearly the Ganga, and in this area here, the Brahmaputra, which ends up making water available on its route. But let's keep that in mind in terms of what it's going to mean in terms of implication. So this actually is an easier plot to actually understand, but here's the Indus, here's the Amur Darya, here's the Ganga, and here's the Brahmaputra. Well, already India is diverting a significant amount of water down from the Ganga to Kolkata. Brahmaputra, China is looking very seriously at diverting the entire river up to the area where they need it. It's very dry in the Gobi Desert area. So that's what is a real potential for occurrence. Amur Darya, what you got is a whole lot of water being generated from Afghanistan, but that's where all the water within the Amur Darya actually arrives. In other words, all of the water is coming from a glacier here, and they are still trying to grow cotton in the middle of a desert in these countries up here, and the Aral Sea is disappearing. That's all well known. Okay, so we got 90,000 glaciers. They form the headwaters of the Indus, the Ganga, Brahmaputra, and the Amur Darya. And just for example, and this is an alarming feature, but 80.6% of the flow in the Hunza catchment for the end is expected to be glacier melt. So it's going to disappear quickly. 17% reduction in the glacier is expected in the Amudera. That's coming from those areas that are in Afghanistan. So these are huge issues in terms of the implications. Trying to grow cotton in the middle of a desert is not a good idea. So now we've got a whole lot of problems to consider, but let's look at the Ganga more carefully. So here we are in this location here. What's going to happen there? Well, the projections are that 18% of the Ganga and 20% of the Brahmaputra will be disappearing by the year 2100. Not fully, obviously, but substantially. Bangladesh, they're already having huge problems of re-drilling the wells virtually every year. I personally do quite a bit of work in Bangladesh, and they are already having to re-drill the wells. But as you get decreases in the amount of water ending up in the Ganga, and perhaps even, hopefully not, but catastrophically, the Brahmaputra is diverted, Bangladesh is going to have a huge, huge problem. So no countries in the world have as much difficult future ahead as both India and Bangladesh. Bangladesh is already encountering it. India has significant problems, as mentioned a few minutes ago. So, overall implication from melting land glaciers? Well, glaciers are melting, we know that. For many locations, this is currently resulting in more flow. So in other words, yes, it won't disappear immediately, but in the not very long-term future, there will be decreases of that water. Glacier melting will dissipate low flows, and globally, glaciers are expected to shrink by, it's hard to put a dimension on that, but when we look at actually what the implication is to sea level rise, it's really pretty minuscule. It's 0.63 millimeters per year. So keep that in mind also. So the glaciers are very, very important to what they do for us on the surface, but they don't make the sea level rise that is going to be a much bigger concern. If all the glaciers, not including the big ice sheets in Greenland and Antarctica, were to melt entirely, the sea level would rise by about 25 centimeters. But what about the thickness of the polar glaciers? Greenland, the elevation of the glaciers is 3,000 meters. If they all melted, the rise in the seas would be 7.4 meters. Thinking back to that 10 meters that I referred to, where 12% of the people live, that's a big number. If you look at Antarctica, 4,500 meters. And I read this at one point, and then I did the calculation myself, and it is in the right ballpark, 58-meter increase in the rise of the seas because of Antarctica. Well, before we all get panic-stricken, that won't happen for hundreds and hundreds and perhaps thousands of years. But let's look at this one, the Arctic Ocean. Its ice cover is 2 to 3 meters, and it has a relatively insignificant impact on sea level rise. Okay, because there's not a whole lot of water there. So what's happening in the changes in the Arctic climate? They've been large and ongoing. Now, when you have ice, obviously there's a high albedo, so the incoming radiation from the sun is highly reflected back into the atmosphere. But what's actually looking now? Let's look at the Arctic sea ice in 1979. And this is Canada here. This is Greenland. This is Russia over here. And that's the way it was in 1979. Now we look at it in 2020 and take a careful look at that same situation in terms of proximity. Here now, there is open water coverage. Similarly, if you look down here, there is the Northwest Passage, which was so sought after several hundred years ago to allow goods to be transported from Europe to China and backwards and so on. Now we are able to pass through that. So in other words, the Northwest Passage is now passable, very much so. So the Arctic sea ice is changing dramatically because it's very shallow and it's changing quickly. So this is just a schematic picture, but it shows the sunlight intensity coming in and the reflectivity because of albedo. But as soon as you remove the ice cover, no longer is that incoming energy actually being passed back into the atmosphere. It's now melting more ice. So it accelerates the rate of loss of the ice cover. So the albedo is being lost with Arctic ice melting. Increasing percentages of incoming sun radiation no longer being reflected back to the atmosphere. The water's warming, which in turn we get more melt, and the cycle continues. Hence, what you see from the yellow is what it was in 1979, and what you see in 2020 is a very different and obviously very much smaller amount of ice cover. You can see the passageway for the Northwest Passage is abundantly apparent, and that will become obvious in just a few seconds. In fact, what you now see, this is Canada on the left, and we're looking down. You see that clearly on the polar regions, and here's Russia on the other side. But what you can see now is that there is free and open space whereby there is significant traffic of goods and people for tourists in both the Russian side and the Canadian side in terms of transportability. Well, these are examples of what they're looking at. Scenic, absolutely fantastic, but it also shows how much disappearance of the Arctic sea ice is already occurring. Arctic sea ice is now declining at a rate of 13.1% per decade. That's what's happening. And this little bear that's, well, not necessarily little, but this polar bear sitting on this thing is enjoying a few quiet moments, I guess, but look what the vessel is behind them. That's an ocean-going tourist vessel. So 239 cruise ships made their passageway through before May 17, 2020, and the numbers continue. So the warming in the Arctic is changing at greater rates. It's changing 2 to 3 times as fast as the global annual average. With increasing greenhouse gases, the Arctic warms quickly, etc. The troposphere is thinner. It's only about 5 miles thick at the North Pole. Therefore, the sensitivity or the rate of change is dramatically quickly. Okay, what does all that really mean? Yes, we're losing ice cover and so on. Do we really worry about it? Well, we need to. Vortices are responsible for the dramatic short-term changes in the winter climate we're now experiencing. Polar vortex, it's a large area of low pressure and cold air that surround the poles, and we're interested in this situation in the Arctic. With rising temperatures, we're getting less reflected sunlight, etc. The polar vortex weakens and collapses, and as a result, you move from the condition embodied with the left side of the figure versus the right side, and you can see the strong jet stream is keeping the cold air contained within this region. Whereas when you start to see a wobbly jet stream, now you see incursions of large air masses making big changes. Warm air moves north, cold air moves south. Disruption in the stratospheric polar vortex. When the polar vortex is weak, Arctic air pushes out onto the jet stream. So the tropospheric polar vortex, a massive fast-moving winds that flows 5 to 9 miles above the Earth in a wavy path, etc., as shown there. And the wave then, the containment is lost, and weather extremes migrate south. Well, you might say, well, does that really matter? Well, here's an example of what the depiction looks like. Obviously, we're looking down at the polar surface, so we see North America in the south portion, Russia in the basically northwest, and Europe in the northeast. What you see is cold air. But now when you see January 2014, now you see a detached part of the polar vortex now being able to move south. And the most dramatic one, the one that has been absolutely massive, is Texas in 2021. This is the largest damage event that's happened in the U.S. history. $130 billion worth of damage from this one extreme event. What happened was a polar vortex moved down here. It actually impacted such a significant distance that even areas within Mexico, down where the cursor currently is, were under freezing conditions. This is an example then of what it looks like in terms of not just Texas, but clearly in Canada we're quite used to cold weather, but we got brutally cold weather here. My own house was minus 18 Celsius. 278 people were killed. It was the largest damage event in American history. So all the way down from Canada, the US, and northern parts of Mexico. Now, But you might say, well, that's really terrible, but does that really kind of conflict with what we're saying by warming? Well, that same year, 2021, the world had the planet's 16th warmest February since records began. So reflecting the fact you've got a long, 2 week period where it was extremely cold. So what you've got now is extremes. One is when it's going to happen, it's going to clobber a lot of things. And when it's not, it's getting warmer. So on average, it's warmer, but in fact, you had this dramatic shift in temperatures. On average, in other words, winters are increasingly mild because climate change has increased temperatures worldwide. But the polar vortex is becoming increasingly common. That's the scary part of this whole thing. So it's not excluding to North America, but this is the southward shift of the polar jet stream. These people are farmers just west of Delhi. So they got a freak hailstorm in that central and northern India in February and March 2021, clobbering their harvests, totally destroying them. So you might say, well, okay, that's obviously not good, but maybe it's unusual. Well, here is the situation for Eastern Europe, impacted by an extreme Arctic cold blast and snow next week, and as the southern lobe of the polar vortex reached down. So here is the Arctic blast coming down through Russia and impacting Europe. But it's not ended there. This was Christmas 2022. We had what is called a once-in-a-generation severe storm. I only wish it was once in a generation, because this introduced total chaos in the transportation system throughout entire North America. Just minus 18 degrees, minus 20 degrees in places that would be normally minus 10. So dramatic, short term, but nonetheless present. Throughout the US, from this event that hit Houston, they dropped 21 degrees Celsius in 1 hour. So the temperatures changed dramatically quickly, and the impacts were huge. So what are we getting? Well, we're getting more very cold weather for short periods of time. Doesn't mean, however, that the monthly average isn't increasing. In fact, it's overcompensating for the fact that the cold weather was there. This is increasingly challenging to the southern areas. So what do we find from all of this? Well, conclusions. We've got issues of deteriorating water supply opportunities for large cities and crop growth. They are enormous and increasing. We cannot rely upon the groundwater because the groundwater does not replenish itself rapidly enough to make a difference. The infiltration from densely populated cities, that doesn't happen, and all of the efforts that are being used in North America and Europe, etc., that I'm aware of, what they're really trying to do is to keep the water balance at the surface about the same as pre-development conditions. So they're putting in, we call them low impact development, that type of thing, but they're not actually infiltrating any water into the deep horizons. So groundwater withdrawals are in serious trouble because we are drawing out far too much, and the infiltration from densely populated cities is not effective at replenishing it. Population growth, megacities, well, they need for 20 million people, 10 million people, whatever, they need water, enormous quantities. And if they don't get it from surface water or import somehow, subsidence issues are dramatic. So the impact on trying to protect against storm surges is really becoming totally impossible. Seawater intrusion as well to destroy the utility of the groundwater that does exist there. Urban water security issues, well, they're large and rapidly increasing. We're seeing them everywhere. Trade-offs, well, we're trying to protect against floods because we're getting more intensive storms, but the ability to use the groundwater as a water supply source is very limited. We need to look for new technologies to infiltrate deeper soil horizons. But I have been thinking about this for years, and I don't have very many ideas that work really more than just piecemeal. Consideration, we must also consider subsidence and salinity intrusion, because that's just simply what's going to happen if we continue to withdraw groundwater, and the walls, we cannot build them high enough to actually be able to sufficiently protect the burgeoning populations, and sea level rise as well. So I have no trouble scaring the hell out of my students when I teach a course in risk assessment. Water security is going to be one of the most difficult challenges this century. It's going to be very difficult. I don't have any easy solutions. I'd love to see anybody come up with some ideas that would help. Groundwater cannot be a solution without replenishment, and we don't know how to replenish it properly. Adjacent areas are having water redirected to urban areas, so they're becoming dry, those areas that are coincident in the vicinity of the large megacities, but they don't have the water that they used to have. Flooding, it being exacerbated by ongoing climate change. The biggest impact, the biggest damage payout of all of the activities in Canada are on flooding, dramatically higher than anything else. Coastal zone storms are huge and they're becoming larger. Admittedly, in Canada, we don't have so many of those, but we do have some impacts by all means. And we can't build walls high enough to protect coastal cities. Land glacier melting and Arctic Ocean ice cover, it's a very real concern in terms of declining flows as the glaciers melt for the land glaciers, and for the Arctic Ocean ice cover, we're going to see more and more incidents of massive change of temperature over a very short period of time. 21 degrees Celsius in 1 hour is mind-boggling. The role of the Arctic Ocean and the implications of polar vortex needs to be recognized and further studied because we don't really understand it well enough, but it certainly is impacting. I no longer think it's a possibility. I think it's a conclusion. What we've got to do is figure out, okay, what can we do? The residency time, obviously, in the atmosphere of greenhouse gases is hundreds of years. We're already past that point. We've got to figure out what else we can do. Increasing importance and adds more uncertainty how to reflect when our polar vortex is going to take place. We don't get a whole lot of warning, but maybe we better start figuring out ways to create that warning. We need to plan more for variations, the highs and the lows, because it's not going to be a uniform. It's going to be an increase with dramatic decreases in temperature for short periods of time. So averages are not going to be sufficient. We got to look at the highs and the lows. We aren't going to run out of issues to address. I keep getting asked, when are you going to retire? And I'm not worried about running out of things to do. We have a lot to do. Water security and climate change, we got to address it better than what we've been doing. So for water security, there is no average condition. And it's going to be one of the most important issues in the 21st century. So with that, don't let the drop go to waste and open it up for questions or whatever else.